Our next speaker is Summer Ha from Ohio State University. Summer is a second-year PhD student from the Department of Geography at the Ohio State University. She's also a graduate research associate at the Center for Urban and Regional Analysis. Summer's research interests focus on the intersection of GI science, transportation, geography, and modeling. I'll turn things over to Summer as well.
Hello, hi. Thanks, Tara, for the introduction. And hello, everyone. Thank you for joining this session. And today I would like to talk about how to reconstruct and analyze historical built environments from old maps using semantic attributes as well as graph-based clustering. Next, please. So here is a bit of the background of our work at the Center for Urban and Regional Analysis, also known as CURA. So we have been working on this Ghost Neighborhoods project where we reconstruct 3D models of historical Black neighborhoods that were fragmented during freeway construction in the 1960s in Columbus, Ohio. So all this while we have been building these buildings manually one by one, and it took us about 5 to 10 hours to build just one building. So imagine when we're trying to build for the entire neighborhood or even the city, it becomes very time consuming. So here's the question that we ask. Next, please. Can we actually extract enough information from the historical maps, especially just from the building footprints themselves, to help us generate plausible 3D models in a scalable manner? And this is when urban morphology becomes essential to us. Next, please. So a quick overview, urban morphology is the study of the physical forms and the spatial arrangements of the built environment. It is very essential to help us understand how past decisions made on historical built environments continue to shape our life today and even inform the planning for the future. And most of the time, urban morphological study is about identifying groups of buildings with similar characteristics. Next, please. So conventionally in urban science, there are many studies that trying to quantify the built environment using numerical measures like parameter, height, area, and so on. While this method works for many other cases, it does not apply to us because when we try to do 3D modeling, imagine we have two different footprints. One is a square footprint, and then another one is like a circle footprint. They might share the same area, but they just look differently in terms of their geometry and their topological characteristics. And these are important to us when it comes to 3D modeling. We also realized that many studies have been using remotely sensed data to do 3D modeling of contemporary built environment. Unfortunately, we just can't go back in time for more than half a century ago to collect the information from our historical built environment. So this makes our historical built environment and the appropriate methods to study them remain underexplored. Next, please. We also look at some work in computational science and geoinformatics fields, and we realize that many works or studies in this area, they have been using a shape-based approach to cluster building footprints. So for instance, if we look at the two polygons in the middle right of this slide, imagine on the left, it is actually like a one-story warehouse made of brick. And then imagine on the right, it's a 1 or 2-story dwelling made of wood. By just looking at the shape itself, we wouldn't know this kind of semantic attributes that will affect how they look three-dimensionally. So we need all the semantic attributes. Next, please. So the objectives of this work is to first, we unlock the data in old maps so we can study the urban morphology of our historical neighborhoods. We are specifically focusing on using historical Sanborn fire atlas maps. And then next, please. And then we will cluster the building footprints from these Sanborn maps based on their shapes as well as their corresponding semantic attributes. Next, please. And then we will convert this building clusters into parametric templates so that we can do 3D urban modeling at scale. Next slide, please. And then the anticipated products of this work will be to enable 3D morphological analytics, especially for historical neighborhoods, and also to facilitate VR experience of historical cities or neighborhoods from old maps. Next, please. So this is our study area and the data that we used in our study. We are focusing on Hanford Village in Columbus, Ohio. What we are seeing on the left is a georeference Sanborn map, and on the right is the building footprints that we detected from Sanborn maps. So we had about 1,500 buildings in this study area. They're all made up of residentials, commercials, industrials, and then they're all from different they all have different number of stories, like 1 story, 1.5, 2 stories, and they are all made up of different construction materials like frame or wood, brick or tile, concrete, and cinder block. Next slide, please. So in terms of methodology, we are trying to compare 2 different approaches. The first one is just to look at the shape itself. That means it's the exterior walls of each building footprint. And then we will compare this against our second approach, where we try to integrate semantic attributes as well as we look at the shapes. Next slide, please. So for a shape-based approach, we will start off with a polygonal data preprocessing. Next, please. Where we actually extract all the vertices from each building footprint. Next slide, please. And then we will generate the skeleton from the vertices for each building footprint. Next slide, please. And then from this skeleton, we convert them into a graph by accounting for the spatial attributes of each building footprint, including the weights for the vertices as well as for the edges. Edges is like the length between the vertices. Next slide, please. And then we will compute the pairwise distance between graphs using an optimal transport theory. Basically, we are just trying to compute the number of operations needed to translate graph 1 to graph 2. And the number of operations will give us the distance between 2 graphs. So that gives us a nice distance matrix between different graphs. Next, please. And then we will do a graph-based clustering using the eigenvectors of the distance matrix. So eigenvectors is a set of numbers that we use to characterize a matrix. Next, please. For the second approach, we are integrating semantic attributes in our workflow. So we will start with doing semantic data preprocessing. So with our data set, we will sort them according to 3 main attributes, including building use, number of story, and construction materials. And for each unique semantic group, we will plug them out and we will do the shape-based approach for each of them. Next, please. So this is just to show how we actually use silhouette analysis for us to do internal validity, where we actually evaluate how well each point fits in its own cluster compared to the other cluster. So the image on the top right, it basically just shows the distribution of the buildings in their assigned clusters as indicated in different colors. And then on the bottom left, that's a silhouette plot. So on the x-axis, it is the silhouette coefficient value ranging from -1 to 1. So if we get any values closer to 1, that means the points fit in very nicely within their own cluster. But if we see any negative values, that indicates some potential misassignment of cluster. And then on the y-axis, it's basically just to list out the different clusters as indicated in all these color bands. The thickness of these bands represent how many buildings we have in each cluster. And the vertical dashed line is an indication of the average silhouette score. So basically, the average silhouette score is an overall mean of all silhouette coefficient values, summarizing how good the clustering is in general. So ideally, you would like to see all these different bands touching the vertical dashed line. And then bottom right is just a 2D embedding space of clustering, where we would ideally like to see a compact, well-separated blobs of points. Next, please. So this is an overview of the results we got from our first approach, where we just focus on the shape, the exterior walls of the building footprints without doing any semantic sorting. We have about 15 clusters in this result with an average silhouette score of 0.335. That is kind of moderate. So we also did external validity by sampling some buildings from each cluster and compare them against ground truth from Sanborn maps by looking at their building footprints. And also we sample some ground truth from street level photos from parcel data. Next, please. So these are a few examples that we got from cluster 11. We can see that based on the footprints, the building footprints, buildings in this cluster, they are mainly characterized by a rectangular plan with two projections. And that seems to be pretty consistent in their 3D appearances as well. They're all two-story buildings, and then they have a front porch. The only difference is their roof geometry, but this is something that we can set as a parameter with our template for modeling in our software that we use for 3D modeling. Next, please. And then the second example is from cluster 0. In this cluster, most of the buildings, they are characterized by a simple rectangular plan. But as we look closer at the building footprints, they are all made up of different types of buildings. We have the first and second examples, they're dwelling. And then the third example is an apartment. And the fourth one is a garage, an automobile garage. And they all just look so different for us to just summarize them in one or two templates for 3D modeling. Next, please. So this tells us that it is important for us to sort them according to their semantic attributes before we start doing clustering. Next, please. And now we are looking at the overview of the result from our second approach, where we do semantic sorting before we do shape-based clustering. Specifically, we're looking at a two-story multifamily dwelling made of frame or wood. So with this 123 buildings, we have 3 different clusters with an average silhouette score of 0.588, which is a pretty good result. Next, please. So looking at cluster 0, the buildings here are mainly characterized by a rectangular plan with a projection. But if we are looking closer at the building footprints, the third and fourth examples, if we consider the interior lines, there are actually 4 different components as compared to the first and second examples. There are only 3 components. And then for the third and fourth example, the projected part is actually at the back of the building. And then the front of the building is actually, they have a full width front porch. But for the first and second examples, the projected part is actually a partial width front porch for the building. So next, please. With this example, we can see that the interior lines of the building footprints, as well as the order of the components, are very important for us to know how to model the buildings. Next, please. For cluster 1, we can see that the buildings are characterized by a rectangular plan if we just imagine the exterior walls of each building footprint. But the same patterns are happening. The same pattern is happening here as well, because for the third and fourth example, they actually have a front porch. But if we just look at the exterior walls, we wouldn't know there would be a front porch. Whereas the first and second, there's no front porch at all to the building. Next, please. So this again tells us interior lines are very important for us. Next, please. And then for cluster two, the buildings from this cluster, they are made up of rectangular plans with two projections. This is pretty consistent in terms of their building footprints and how they look 3D, three-dimensionally, and it's just the difference in their roof geometry. So this is something that we can easily play around with the parameters in our parametric templates eventually. Next, please. So to summarize, we tried a shape-based clustering approach where we just look at the exterior walls of the polygons of the building footprints without any semantic sorting, but it is not sufficient to tell us the semantic differences between different buildings. Like we have garages, apartments, and multifamily dwelling in one cluster, and it wouldn't help us with finding the optimal number of templates for 3D modeling. And then the second point is that we integrated semantic attributes into the shape-based clustering method. And we were able to show that even within a semantic group, we were able to have different morphological clusters to inform us how many templates would be optimized and we need to build. But even so, we realized that it is still not enough to help us differentiate simple polygons and multi-part polygons. Next, please. So to conclude, we demonstrated some limitations from the existing clustering methods, especially for our case when we try to do 3D modeling. We cannot just cluster them based on any numerical measures or any shape-based method. And we also showed that by integrating semantic attributes into shape-based method, we were able to improve the identification of building morphological cluster. Next, please. So future directions, we are planning to, right now we are working on including the interior lines into our clustering methods, and we will see if that helps to improve the performance. And we will also consider including the order of components as well. And then we will have to develop a scalable methods to help us conduct external validity. And finally, to start working on these different templates based on the morphological cluster and their architectural elements. Next, please. And thank you so much for your attention. And any questions are welcome. Thank you.
Thank you, Summer. We do have time for maybe a one question. So one of the questions that came in was, this is a very exciting project. Are there certain types of buildings on the Sanborns that are easiest to analyze and integrate? Are there types of buildings that are especially difficult?
Yeah, thank you for the question. So the easiest part would be just a simple polygon where they only have four vertices. The most difficult part would be when they have too many different polygons, like multi-part polygons, footprints. Those are the more challenging one. And we also have this challenge in like some industrial buildings. We can imagine they will be more variances in terms of how they look, because like right now we are experimenting with residential buildings where most of the time they're just like cookie cutters, but for commercial buildings it will be more different, and then we will try to extend our work in those areas too. Thank you.
Thank you, Summer. We really appreciated your presentation today.